Hi, my name is Amitesh Kumar Shah, and today I'll be explaining how nonlinear thresholding function is found from penalty function. The thresholding function can be used for denoising by applying it to the transform domain representation, provided the transform domain yields a sparse representation of the signal. The use of sparsity in signal processing frequently calls for the solution to the more general problem. Here, phi of x is the penalty function and it should be chosen so as to promote sparsity. And to better understand the role of penalty function, it is informative to consider the scalar case. So, where y and x both are scalar and y is the input signal and phi of x is the penalty function and sy is the shrinkage function. So, it shrinks y towards 0. So out here we are given y and we are required to find x so as to minimize the function, and we'll be considering two particular cases, one with phi 1 of x equals to lambda x and another phi 2 of x equals to 0 and 1 when x equals to 0 and 1 when x is not equals to 0. So here lambda is greater than 0 and x is a convex function. So we to find shrinkage function we should minimize f of x, and it can be done by taking a derivative. So by differentiating y minus x square, half of y minus x square, we get a straight line. And by differentiating a convex function of lambda x, we get a signum function. As it is not differentiable at x equals to 0, as it is not differentiable out here, so it forms a straight line, and this in turn gives me a soft thresholding function. And thresholding function, it sets small values to 0 and it also shrinks the remaining value or larger value. So it sometimes leads to the loss of information. Second case is when phi of x is 0 at x equals to 0 and 1 when x is not equals to 0. Again we have to minimize the function so as to find x so with respect to x. So there is a y minus x square and there is a penalty function. Out here there are two cases. When lambda is greater than y square by 2, it forms this kind of curve, and when lambda is less than y square by 2, it forms this kind of curve. So when out here the minimum value is lambda and out here the minimum value is y square by 2. So the resultant thresholding function looks like this, and so whatever value greater than under 2 lambda is the same as the original value, but value between minus under 2 lambda to under root 2 lambda is set to 0. It is also sometimes called keep or kill method, and here we'll be discussing if there is a noisy signal G which is formed from a noise-free signal X and a Gaussian zero mean Gaussian noise signal is added to it. In transform domain, it gives a noisy coefficient. W is the wavelet coefficient of the noise-free signal and N is the noise. So here the key point to remember is the linear transformation of zero mean Gaussian random signal results in zero mean Gaussian random signal. So out here goal is to estimate wavelet coefficient noise free from the noisy observation Y. There are three ways in which you can determine the threshold value. There is a practical way in which the signal is unknown and we seek approximation of the signal that is smooth and fits the input well. Second method is the optimal method that takes the noise threshold as a noise variance, and the third method is the universal method in which the threshold is equals to variance into under root 2 log n, where n is the sample size. So I'll be I'll be showing how a wavelet based noise reduction by using thresholding. So out here our input signal is a skyline and we add a zero mean Gaussian noise to it with a variance of 0.1, and this is the noisy signal, and Here will modify the signal in wavelet representation by thresholding. So we this is the wavelet representation. I did a 3-level half wavelet decomposition, and uh, so we this is the final result. This is the original noise free signal, and this is the noisy signal, and compare with the noisy signal, we comparatively obtained a better result as all the noises are removed, as large amount of noise is removed. However, in a hard threshold, we can see there are these noise spikes that is not present out here. This is due to the small values that are slightly greater than the threshold value. So by using a soft thresholding, we can shrink those value towards 0. This in turn reduces the spurious noise spikes that it was suffering from. Thank you.